Hello everyone. In today's video tutorial we are going to perform a very interesting and playful simulation. We are going to simulate a slingshot. Although it seems to be a funny video, we are going to discuss and demonstrate various tips and tricks in Abaqus user interface that will be for sure useful for some of your next analysis. So let's start. I have already run some cases, some similar cases, and I'm going to show you one new step by step. Let's import the SAT file with the assembly that we have created in the CAD software, and you can see here that there is some issue with the geometry, but you can click ignore invalidity and you can see later that the simulation will run. So let's create our materials. We will create a wood with a density of 0.7 -9 and an elastic properties, a Young modulus of 10 gigapascals. We put a value of 10,000 megapascal because we're working in millimeter, and the Poisson ratio. And now we're going to create a material for our rubber band, a density of 1.2 -9, and here we are going to include hyperelastic properties. We are going to use the Manor-Rivlin model and click here the coefficient, and let me check my notes. I will assign the following values. 0.133 and perfect. So now let's create the relevant sections for wood, homogeneous solid, and select the wood material and the rubber one. Perfect. So now we have to assign our sections in our geometries. Here this is a rubber band, and this is made of wood, and let's say that the sphere is also made of wood. Perfect. So when you have a geometry of a sphere, it's very useful to make some partitions for a better mesh. Perfect. Not perfect. And not perfect as well, but no problem. Can go back here under the tree, delete this datum, and let's create a datum using this option with 3 points. 1, 2, 3. Perfect. And since we have not other points, let's create these options offset for this from this plane value. Let's say 20. It's okay. Let's see it. Nope. Let's go back here in the tree, click edit. 190. I think it's okay now. So now here we have these datums. We can make the partitions in our geometry using datums. 1, again click, right click, select all the cells now, datum, yes. Again, datum, yes. So if I go to the module, the mesh module, you can see this green color, perfect. Let's click 2.5. Let's select them and click explicit. Okay, let's leave it as reduced integration for the ball, for the sphere. Yes, nice mesh, perfect. So here in the handle, okay, we can create. Let's create the datum. Okay, perfect. One datum only, and this will help us for the boundary condition assignment. Okay, perfect. Let's use tetraedra, tet elements for this, because the geometry is quite complex and it's not so easy to mess with bricks, but it's not a problem. Okay, tet element, explicit, perfect. Let's assign a value of 5 for the mesh. Okay, we can select the handle this and make it a little more dense and more coarse, the mesh. And let's mesh it. Okay, it seems okay. So now let's do the same for the rubber band, the tetrahedron elements as well. A very difficult geometry here, this radius for hex elements. Explicit, modified simulation, and let's define a little bit the global size, 5. Let's check it. Okay, I think it's okay. Okay, now we can move forward and go to the assembly. Let's create our instance by including all 3 parts. You can see that they are created as an assembly, they are imported as an assembly, and they share the same coordinate system, and the job has been done in the CAD software, so we can quickly move forward and create our step. So now what I'm thinking to do is to include 2 steps in my analysis. So let's create the first step, 0.550 millimeters. Let's assign a mass scale criterion, scale to a target increment. Let's start with 4-7, and let's create a second step where we are going to deactivate the displacement of the ball, and let's leave it 0.2. Okay, perfect. So we have to ask for the output request. I'm usually asking values after some units of time. I will not ask for the strains or for the force and reactions. And okay, if you exclude some values, the ODB file that will be generated, it will not be so big in memory. Same. Okay, let's ask for the percent of mass for the mass scaling. Let's create a second for the next step. The value of 2 and ask for the stresses, the S-misses, and only the translation here. Perfect. And here ask for some energies values, the total and formats. Perfect. So now for the explicit, we can go to interaction properties. I'm using the penalty method with the coefficient of friction 0.5 and a normal behavior of hard normal behavior. Let's create the interaction now. No, let's go back. Creating the first step. So we have to be careful with that because our time step it's not so small, and maybe we will lose some contacts. So if this happens, we have or to make our time increment smaller, or we have to go here and manually include some surface for our contact pairs. For now, let's move forward as it is and create an amplitude for the displacement. So let's put some value 0, 0, and this value is the time of our first step, our duration of our first step, and let's put the value of the unit for the amplitude. And now let's go here, create the boundary conditions from the step 1. Here this will be a fixed support for the handle, and let's create a second one which will be a displacement boundary condition at the step 1 for the sphere, and let's select the sphere, perfect, and let's assign a boundary condition on the third axis, Z axis, U3, and minus, let's say 150 millimeters. And now here in the amplitude, we have to include the amplitude that we created previously. Perfect, you can see the arrows that the boundary condition has been assigned correctly. So the final thing that we have to do is to create a load for the gravity. Perfect, step 1, and this will be in component with the y-axis, minus, since we're working in millimeters, minus 9,810. Maybe you can see the arrow. Yes, here is the arrow, center of mass. Perfect. But now we have to do one last thing. We'll go here to the boundary condition manager, and we have to deactivate the displacement boundary condition of the sphere in the second step. We have to leave our ball, our sphere free to move forward. Okay, perfect. I think that everything has been set up correctly, and what we have to do now is to create a job. You can see that I have already run some models. Parameters B. It's okay. From here you choose the processors and click OK. Right click and submit. So now I will show you some results from my previous analysis, same analysis which I have run it before. And very quickly I will show you some results. Perfect. Okay, let's leave it as it is. So guys, you can see here we're at the step 1. Very, very nice. Now step 2. I hope you like my video and stay tuned for next videos. Thank you for watching.